In the previous lecture, we have discussed the quantum theory of ferromagnetism. Actually, this quantum theory is based on the classical theory which was provided by Weiss. And Weiss had assumed an internal field which is also called internal molecular field or Weiss field to explain the spontaneous magnetization of ferromagnetic material. And actually on the same line in quantum theory too, we also assume the internal molecular field postulated by Weiss. Okay? And after considering the intermolecular field, we explain all the basic features of ferromagnetism. Okay, but why this internal molecular field is produced? What is the region of its origin? Okay, or you can say that in which thing its origin is rooted. Such a problem was not dealt by Weiss, actually. In fact, the problem of the nature and the existence or origin of this internal field was actually thought by a famous scientist Heisenberg. And actually Heisenberg interpreted this molecular field in terms of exchange interaction between electrons. So this is also called Heisenberg interpretation of Weiss field. How we can actually interpret the Weiss field, that was not provided by Weiss himself, but this is due to the most famous scientist of quantum mechanics named Heisenberg. Okay? Actually, you know that ferromagnetism is caused not by the orbital motion or orbital angular momentum of the electron, but it is due to the spin of electron. In fact, when a spin interaction takes place, ferromagnetism arises. So, taking this very idea under account, Heisenberg proposed that inside a ferromagnetic material there is an exchange interaction, and that exchange interaction is the cause of Weiss internal field or Weiss field. Okay? Actually, when you talk about this exchange force, what is this exchange force actually? In fact, exchange force is essentially caused by the purely electrostatic Coulombian interaction. And its magnitude can be much larger than that of the magnetic interaction. Okay? And in fact, this exchange force appears in the form of a spin interaction, as I have told you earlier. Okay? In fact, the strength of the interaction depends on the separation between the interacting atoms. Okay? And as the distance between two atoms changes, let us say this is atom number A and this is atom B, and if they move towards each other or away from each other, that is the distance between them changes, then actually the sign of this exchange interaction also changes. Okay? In fact, it is found that when the two atoms, actually here this word electrons must be replaced by atoms. Okay? When two atoms, not electrons. Okay? When two atoms approach each other, the electron spins of unpaired electrons in each atom assume parallel orientation. Okay? And if interatomic separation decreases, more and more, the exchange force decreases until finally they pass through zero separation and anti-parallel spin is favored. So actually in case of the two interacting electrons, the spin also changes with the distance between the electrons or the atoms containing the electron. In fact, when the distance between the two atoms is actually decreased, then there is a flip of spin. Okay. So actually the strength of interaction depends upon the interatomic separation, as I have told you, and it may change its sign as the separation is varied. And it can be predicted that as the two atoms approach each other, the electron spins of unpaired electrons in each atom assume parallel orientation. And if interatomic separation decreases more and more, exchange force decreases until finally they pass through zero and an anti-parallel spin is favored. Okay? Actually, this situation resembles with that which we found in Heitler-London model for a hydrogen molecule, where the configuration of parallel spins is very unfavorable compared to the configuration with anti-parallel spin. Okay? So actually Heisenberg developed this exchange theory for explaining the Weiss field on the line of Heitler-London theory of hydrogen molecule. Okay? So we will make calculation for the interaction energy due to the spin-spin interaction on the basis of Heitler-London theory of hydrogen molecule. You can see in this figure, actually here I have shown this A and B, two small spheres. Actually these two small spheres marked by A and B represent the two atoms. Okay? And this one, a small very tiny sphere, this actually represents the electron. Okay? And of the first atom. And similarly, this 2, which is also represented by a very small sphere, just like a point, this is the electron of the another hydrogen atom, let us say B. Okay? And now you can see, I have considered that the separation at any moment between the atom A and the atom B is RAB. Okay? And the separation between these two electrons has been assumed R12. Okay? And the separation of the electron number 2 of atom B from the atom A is Ra2. And the separation of electron 1, which is electron of atom A, from the atom B has been assumed Rb1. Okay? Now there will be actually four electrostatic interaction here. You can see the nuclei of the two atoms A and B will interact one another via Coulombian interaction. Okay? And after that you can also see that these two electrons will also interact one another electrostatically. And there will be an electrostatic attraction between the nucleus of atom A and the nucleus and the electron number 2 of the second atom. And similarly, another electrostatic attraction will be between the nucleus of atom B and electron number 1. Okay? Actually, the interaction between the nucleus of first atom and its electron, the nucleus of the second atom B and its electron has been neglected here because these interactions will cancel one another. Okay? So following the Heitler-London theory of hydrogen molecule, the interaction potential or potential energy between the two atoms can be written like this. You can see if VAB is the interaction potential, it means interaction potential energy. Then in CGS unit, you can write that VAB will be equal to E square over RAB. This is potential due to the interaction between this atom A and atom B. Okay. And you know the charge of this atom is, nucleus of atom A is plus E and that of B is also plus E. And charge of electrons are minus E and minus E. Okay. Then this is actually repulsive interaction, so potential will be positive. And again, the two electrons 1 and 2 will also repel electrostatically one another. So this interaction, due to this repulsive interaction, the potential will be positive. And what will be that? That will be E times E, that is E square over R12 in CGS unit. In SI unit, you have also to divide this factor by 4 pi epsilon naught. Okay. So the second term is E square over R12. Okay. Now, there will be attractive interaction between the nucleus of atom A and the electron number 2 of atom B. Okay. And that will be, so the potential due to this attractive interaction will be actually negative, because this is attractive interaction. Okay. This is repulsive interaction. You can see this is repulsive, but this is attractive interaction. This is also attractive interaction. Okay. And so the net potential due to all the interactions, which all are actually of electrostatic nature, this is E square times 1 over RAB plus 1 over R12 minus 1 over RB1 minus 1 over RA2. Okay. As I have told you that this A and B subscripts actually denote the two nuclei or two atoms, we can say, and this number subscripts 1 and 2 has been used actually for electrons. Okay. Now, the energy of this system can be written like this: E equal to K plus minus J. Actually, here this K is the Coulomb interaction energy. Okay. And JE is exchange interaction integral, or you can say that this is energy due to the exchange forces acting between the spin due to the spin interaction between the electrons. Okay. So E is given as K plus minus JE, where JE, as I have told you, that this is called exchange integral. Actually, in quantum mechanics, this exchange integral JE is defined like this. This is just its definition, but we will not have any use of this equation. This JE is given as integral of this psi A1 times psi B star 2 VAB psi A2 psi B1 dV1 dV2. Actually, dV1 dV2 are the elementary volume. And this psi B star 2, this is actually complex conjugate of psi B2. In fact, this psi A1 and psi A and psi B, these are actually the atomic wave functions of electron 1 and 2. When you write the number 1 in the bracket, that represents the atomic wave function for first electron, and 2 refers the atomic wave function for the second electron. Okay. Now, actually, this plus minus sign has been taken here because this exchange integral may be positive or negative. Actually, when it is positive and when it is negative, that depends on the spin of the unpaired electron. Actually, the positive sign in this equation is for the state of anti-parallel spin. When the spin of the two interacting electrons will be anti-parallel, then actually the sign of J will be positive. Okay. But if the electron spins are parallel, then Je is negative. Je is negative. And actually this anti-parallel spin refers the non-magnetic state of the system, not magnetic state. But the negative sign is for the parallel spin state, which is a magnetic state. So actually in parallel spin state, the energy will be least, energy will be lower, and so the stability will be larger. Okay? And so the system favors the parallel spin state. Okay? And as we are talking about the stable system only, so you can say that for a stable system, this Je must be positive. Okay? Je must be positive. It means here must be there must be here minus sign. And this minus sign will exist only when Je will be positive. Because when J is positive, then you can say that if the total energy will be K minus Je, then this K minus Je will be less than K plus Je. If Je is plus, then K minus Je will become plus. Okay? And if energy is lower, you know stability is larger. So the system favors this state. Okay? Actually, in present discussion, we are concerned with the exchange energy and not with Coulomb interaction. So actually, this energy due to this Coulomb interaction can be taken as a constant factor, because our main concern is regarding the energy due to the exchange forces. Okay? So, considering the relative orientation of two spins, let us say S1 and S2, we can write the interaction energy, total interaction energy E equal to a constant, where constant stands for this Coulombian energy K, and minus 2Je times S1 dot S2. Actually, here Je, you know, is the interaction integral, exchange integral, and this S1 dot S2, this actually represents the spin orientation, and so when you will multiply by this scalar product of S1 S2 to 2Je, then you will get the interaction energy. Okay? In fact, this result predicts that the exchange energy appears in the total energy as if there exists a direct coupling between the two spins, and therefore exchange interaction between electrons with spin vectors Si and Sj will have the form like this, equal to minus Je times Si dot Sj. Actually here this small Si and Sj, these refers the spin of ith and jth electron. Okay? But for two atoms, if you are talking about the total spin vectors Si and Sj, then the total interaction energy can be obtained by summing over this value for all the atoms or all the electrons present in this system. And so the total interaction energy is given as minus 2Ji summation over this Ij Si dot Sj. Okay? And after removing this summation, you can write this equation as capital Si and capital Sj instead of this small si and small sj. Actually, this total energy depends upon the relative orientation of the two total spin vectors Si and Sj. Okay? And this Jij, this is exchange integral for the two atoms. Okay? Actually, the behavior of the exchange integral with the ratio of the interatomic separation, that is RAB, and the orbital radius RO, which which will be taken here as the radius of the third actually third orbital, that is R3d, you can say. So the value of this ratio when plotted in against of the exchange integral, then we will see that when the ferromagnetic behavior can be exhibited. And for this I have shown here in this graphical plot a graphical plot of the exchange integral JE in against of RAB over R3D, where actually this R3D, you know, this is the interatomic separation of the this is a ratio of interatomic separation to the radius of the third 3D orbit. This R3D represents 3D orbit. Okay, and you can see this figure, the behavior of the exchange integral as a function of the ratio of interatomic separation RAB and the radius of the 3D orbit, that is R3D, in against of JE. And you can see from this figure that JE is actually positive for this Fe, CO, Ni and GT. Okay, and it is negative for this Cr and Mn, that is chromium and manganese. And you know, when Je is positive, then actually the attractive interaction takes place and the system is stable. So one fact is also obvious from here, that the value of this RAB by 3D is much greater than 1. Okay, in fact it has been found that the value of this ratio RAB over R3D is never less than 3. Okay, for these Fe, CO, Ni and Ct. Okay, so Fe, CO, Ni and Gd, for which this Je is positive, you know, such materials are actually ferromagnetic materials. They exhibit ferromagnetism. But the materials for which this exchange integral Je is negative, that is for Cr and Mn, those actually do not exhibit the ferromagnetic behavior, that is no spontaneous magnetization will exist in this. Okay. Now after knowing this exchange interaction, we will now see how the exchange integral Je, the Weiss constant lambda and the ferromagnetic Curie temperature theta F are related together. Our aim is to relate these three parameters. Okay. Actually, a well-known scientist, Stoner, has suggested a simplified procedure to set up a relation among these three parameters, Je, lambda and theta F. Okay. Now let us see this equation number 4. Actually, on the basis of this equation 4, see this equation, we can write here the exchange energy of an atom I with its neighboring atoms. Okay, because in this interaction it is assumed that any atom is interacted only with its neighboring atoms. So if you consider any atom, let us say I, and this is interacted with its neighbors, then what will be the interaction energy? On the basis of that equation 4, which we have learned earlier, we can write that this energy is given as V equal to minus 2Je times summation over J Si times Sj. Okay. Actually here the summation extends over the nearest neighbors of atom I only. not the atoms which is far away from I. Okay. Actually, according to Stoner, the instantaneous values of the neighboring spins may be replaced by their time averages. And thus, if there are n nearest neighbors, then this V can be given like this. This was suggested by the famous scientist Stoner. That is V equal to, if there are n nearest neighbors, then V is given as minus 2n times Je Sxi times time average of Sxj. Actually here Xxi, this is the x component of the spin vector Si, okay, for the ith electron, okay, and Sxj, this is the x component of the spin vector of jth electron, okay, and similarly plus Syi times average of Syj plus Szy times average of Szj. And here all the terms has been written actually for this sign of summation, you can see. Because you know, if you will take the components of these Si and Sj, and after that you will take the scalar product, what will be the result? You know that A dot B is equal to what? That is Ax times Bx plus Ay By plus Az Bz. Okay? So, on the basis of this definition of a scalar product, you can write Sxi times Sxj. Okay, just like Ax Bx. But instead of taking the sign of summation, and if you know the total number of nearest neighbors, then according to Stoner, the result will be same as you will take the time average of one of the components. Okay. So instead of this equation 5, in accordance with the suggestion of Stoner, we can write V equal to minus 2nje times this much. Okay. Now let us consider that the magnetization is along the z direction. In fact, generally we assume that the magnetic field is applied in z direction, and if magnetic field will be directed in z direction, magnetization will be also developed in z direction. And if magnetization is z direction, then the x and y components of the spin vector will be 0. So you can say that the average value will be 0. Average value of Sxj, Syj are equal to 0. But what will be the time average of z component of S for j? That is equal to m over g n mu b. Here m is the magnetization, you know. I have not written it, but you know this is the well-known symbol. You have watched so many videos or so many lectures. So now it is well known to you that this capital M represents the magnetization. And can you say that what is this small g? This is Lenz's splitting factor. And this is the number of atoms per unit volume. And mu b is well-known constant known as Bohr magneton. So the time average of Sz, J, this is equal to m over g times n times mu b. Okay. Now let us make the use of the values defined in this equation 7 in equation 6. Okay. You can see, since this time average of Sxj is 0, so first term will vanish. Time average of Syj is also 0, so second term will also vanish. Only the third term will remain here. And so you can see V will be equal to minus 2nje times Szi times time average of this, but time average of Szj is equal to this much. So instead of that we will write this, and so you can see V will be then given by minus 2nje times Szim over G times n times mu b. Okay. So this is the potential energy due to the interaction. Okay. But this potential energy must be equal to potential energy of a spin I in the Weiss field lambda m. Okay. So what will be the potential energy of a spin I in the Weiss field due to the interaction with the Weiss field? Here you know G times Szi times mu b. This is actually the magnetic moment due to the spin. Okay? And when you will multiply the magnetic moment mu with the magnetic field with negative sign, then you get magnetic potential energy. So here minus sign is due to that convention, and lambda m is the Weiss field Hi. So this interaction energy, which has been defined in equation 8, on the basis of this idea can be written as V equal to minus G Szi. Szi, this is the Z component of ith spin, okay, times mu b. And this product G Szi mu b, this is actually the magnetic moment in Z direction. This is the Z component of magnetic moment, you can say. And when you will multiply it by the Weiss field, which is Hi, and that is equal to lambda m, then you get the potential energy. Okay? But we have already defined the potential energy here. So instead of V, you can write the expression for V defined in equation 8. And so this is minus 2nje Szim over Gn mu b, and that will be equal to this much. Okay. Now you can see here this m and this m will cancel out. Okay. This m and m will cancel out. Again, you can see this Szi will also cancel out. Okay. And therefore, from here you can define the Weiss constant lambda. And the Weiss constant lambda, you can see this will be equal to 2nje divided by n times g square times mu b square. So this is the relation between the Weiss constant lambda and the exchange integral j. And from this result you can see that this lambda is proportional to j. Okay. This is this is the relation between lambda and j. Okay. Now to relate theta with j, you have to remember a result which you have learnt in case of the quantum theory of ferromagnetism. When I have discussed quantum theory of ferromagnetism, our final result was for the ferromagnetic Weiss temperature. And you have seen in that video that the ferromagnetic Curie temperature, theta f, this is given as j plus 1 over 3j times lambda and mu j square over kb, where mu j square has been written instead of this much, mu b square, g square, j square. You can see the video on quantum theory of ferromagnetism, and you will see that this is the final result for the ferromagnetic Curie temperature. Okay. So now let us use this value of mu j square here and simplify the equation. So you can see that theta f is given as j plus 1 over 3j times lambda n over kb. And instead of mu j square, now I have written this j square g square mu b square. Okay. Now let us see. One of this j will cancel from here. Okay. And so this theta f will be given by j times j plus 1 times lambda n times g square mu b square over 3 kb. And therefore, this 3 kb theta over lambda is given by this. Okay. Here you know that this capital J is the total quantum number. But since magnetization of ferromagnetic material arises due to the electron spin rather than due to the orbital motion, so here we will not talk about the total angular momentum quantum number J, because the problem which we are going to discuss here, that is due to only the spin of electron. Ferromagnetism is caused by a spin-spin interaction. So definitely we have to neglect the orbital angular momentum vector. So J is as equal to L plus S, okay, L plus S. But here L should be neglected, so instead of J you can write only S. So I have mentioned, you can see, since magnetization of ferromagnetic material arises due to electron spin rather than the orbital motion, and moreover the exchange force appears in the form of a spin-spin interaction, so we can write S instead of J in this above equation. Okay. So you can write that this 3 kb theta f over lambda is equal to n g square mu b square S times S plus 1. Okay. S times S plus 1. Now, we have already obtained the value of lambda here, which actually relate the constants, parameters lambda and j in equation A1, you can see. So let us substitute this value of lambda from equation A1 in this equation at the place of lambda. See here. Okay. So lambda will be replaced by that value. So this is 3 kb theta f over 2n je times this much, because lambda is 2n je over this much. Okay. So in multiplication this will be in numerator, and that is equal to this much, you can see. Now you can see that this n g square mu b square will cancel in both sides. Okay. And therefore you can say that this kb theta f over n je, this will be equal to 2 times S plus 1 over 3. And this is actually the relation between the ferromagnetic Curie temperature theta f and the exchange integral je. Okay. And from here it is also clear that this theta f is proportional to j. Okay. Actually, it is found that for all the three structures, that is simple cubic lattice, BCC lattice or FCC lattice, for which S is equal to 1 by 2. When you will find the value of this factor, kb theta f over nj, what will be that? You can see this will be 2 into 1 by 2, this S is half, and 1 by 2 plus 1 over 3. And this will be simply equal to 0.5, as you can see. Okay. But actually the more exact quantum statistics give somewhat different values And according to two very famous scientists, Rusbrook and Wood, it is found that when we use the exact quantum statistics for finding the value of this ratio, then it is equal to 0.280 for simple cubic lattice and 0.325 for BCC lattice and 0.346 for FCC lattice. And you have to remember these numerical values. Actually, these calculations also enable us to find the value of Je for BCC iron with S equal to 1. With S equal to 1 and for BCC iron, the observed Curie temperature is theta F equal to 1093 Kelvin for iron. This is the Curie temperature. Okay. And when you will take S equal to 1 for this BCC Fe, then it is found that the exchange integral Je has a value equal to 1.19 times 10 to the power minus 2 electron volt. Okay. So I think now the explanation of Weiss field by Heisenberg on the basis of exchange interaction is clear. Okay. Thank you very much.